Hi guys, this is Nitin from FTC Team 18172, Uplift Robotics, and in this video, we'll take a closer look at topology optimization in Creo. In order to understand what topology optimization is, we'll first need to understand the underlying analysis, which is finite element analysis, or FEA for short. FEA is a computerized simulation software that can be used to simulate how parts would behave in real-world conditions. FEA can do a variety of analyses, such as structural, thermal, and modal, just to name a few. FEA is commonly used by professionals and large companies in order to verify if their designs are up to the requirements for each of their products. Using FEA significantly cuts down on manufacturing costs and time because designs can be verified before even making them. Creo has its own FEA application called Creo Simulate that comes when you install Creo. There's also Creo Simulation Live, which gives real-time analysis. However, this requires a good graphics card. Utilizing FEA, topology optimization and generative design can automatically create designs for your models. These two softwares differ from each other in several ways, but at their core, both utilize FEA in order to create the optimal design for parts. Topology optimization creates the most efficient design by reducing the model through repetitive simulation based on some input criteria. In FTC, this is most useful for limiting the weight of fabricated parts by creating pockets within the parts. On the other hand, generative design uses AI to create and remove geometry for your models in order to create the most optimal design. Because generative design can also create geometry, it is far more powerful than topology optimization. Topology optimization and generative design are rapidly expanding fields in CAD, so by no means are our team experts in understanding the complexity behind the software, but we've gained a relative understanding on how to utilize this tool for FTC. Currently, only topology optimization is in Creo, but Creo 7 introduced generative design, which will hopefully be available to students soon. If this feature is made available to first teams, let us know in the comments if you'd like to see a video on this new extension. But in this video, we'll take a closer look at topology optimization extension within Creo. The topology optimization extension is not pre-built into Creo, and there's an extra customization within the PTC installer. So once you're on this application screen, there's a customize button right here, and that pulls up a new window for the different softwares. If you go to Creo Parametric, there's an option here for topology optimization. In order to install topology optimization, you must have Creo Simulate installed. For first teams, you should use the premium standalone license of Creo, and that will allow you to install Creo Simulate. I already have mine installed, so currently the topology optimization is grayed out, but you can simply select it here and continue installing your software like normal. We also have a video on the process of installing Creo, so check that out for more details. Alright, so for this video, I'll be using the outer drive plate from the drivetrain that I've been creating in the past couple of videos, and use it to perform a static structural analysis to generate pocketing geometry for my drive plate. So in order to get to the topology optimization extension, you can go to the Applications tab and select on Topology Optimization. Within Topology Optimization, there's a fairly linear workflow in order to set up an analysis for your model. So from the ribbon, you can simply start working from left to right and define each of the setups in order to create an optimization study at the very end. So these first few commands over here are also in common with Creo Simulate, so any constraints or loads done in Simulate will carry over to topology optimization and vice versa. So the first thing I'm going to do is create a load. There's a few different types, but I'll stick with the standard force moment load. So in order to define a force moment load, you'll need to select the references. So I'll go ahead and select the references that I want using the control key. Once I select all my references, you can go down to the force definition and create the components of your force vector. So for my direction, I'll simply look at the world coordinate system down here, or the WCS, and notice that the orientation of the plate changes. So for the X direction, I'll define a positive value of roughly 100 newtons, and I'll go ahead and change the value as well. I know this is an arbitrarily high value, but I can always go ahead and edit the value later on. So I'll go ahead and click OK. So the next thing I'll do is create a constraint. So I'll go over to the constraints and click on displacement constraint. And once again, I need to select the references. So this time I'm going to click on the standoff holes and use the Control key to select all of the standoff holes, including the bearing holes that I defined in the middle of the plates as well. The next step is to define a surface or volume region which can be used to exclude certain areas from the study. I already have some defined, but you can always use the command and use the standard part creation features such as extrude, revolve, and sweeps to create your volume regions or surface regions. Next, I need to assign a material to my drive plate. So I'll use the material assignments command, and it automatically selects the material because I already have my mass properties for my drive plate defined. So I'll go ahead and just click OK. But you can always use the more command and use the materials database. Next, I want to create an analysis. So I'm going to create a new analysis and set the type to be a structural analysis. I won't bother with the name and description for now though. The constraints and loads that I just created are also loaded up in here. So I'll simply click on them and select OK. The next thing I'll define is the topology region. So the first thing I'm going to define within the topology region is the initial mass fraction. So the initial mass fraction is essentially the amount of the original part that would be left after the study. So I'm going to use a value of 0.6, which means that approximately 60% of the design is retained. But this value can always be experimented with, depending on how aggressive the design should be altered. So the next thing I'm going to define is the excluded volume regions, which is simply the volume regions that I had previously set up. Now I'll look at the options for the different types of fabrication constraints. So I know that I want all of my geometry to be symmetric about all three of the planes. So I'll just go ahead and select all three of the planes, and that looks good. So I'll click OK. Next, I'll define the design objective. I'll leave the response type and objective target as is, but for the analysis, I'll select the analysis that I just created, and I want the goal to be to minimize the weight, which looks good. So I'll click OK. Now I'll need to define the design constraint. So for this study, I'll use the initial mass fraction, but you can always change the constraint values for different values of stress as well. For the constraints, I want the upper bound to be 0.6, which is the mass fraction I set up earlier, and that looks good, so I'll click OK. Now I can click on the mesh, and it should automatically generate a mesh for me. You can always use the mesh controls to control the number of elements that you create within your mesh, but I'll just use the standard mesh. And last but not least, I'll define the optimization study. So this will create a folder in your working directory, so I suggest that you rename this to be something that you recognize. So I'll rename mine to be outer drive plate study. That looks good. And now I need to define the topology region, design objective, and the design constraints that I just defined. Once I'm done, I can hit run, and it'll open up this new window that shows the status of your study. This process can take a couple seconds to hours, depending on how your computer is and the optimization study itself. So I'll come back once this is done. Now that my study is done, I can click on the Show Results button right here, and it will show the results that are created. So I can close out of this, and now you'll notice that it shows the results of my optimized study. Within simulation results, you can get some nice graphics or animations, but you can also take the results and create a new optimized part by going over to Geometry Reconstruction. This will allow you to create an optimized part file, such as the one you see on screen. You may notice, depending on your model, that the geometry created is organic and sometimes might not be able to be manufactured depending on your method. These parts also aren't the most aesthetic, which is why the optimized part should be used to infer areas where geometry can be removed in order to make your model both optimal and aesthetic. As always, the Creo files made in this video will be included in our GitHub repository. If you have any questions about topology optimization in Creo or FTC, let us know by contacting our team through our social media in the description, or leave a comment down below. As always, thanks for watching, and stay tuned for more tutorials in CAD, FTC, and more coming soon.